class, we have discussed about the effect of dilution on the conductivity and molar conductivity. So there we have found, irrespective of strong or weak electrolytes, if you dilute a solution, the conductivity or specific conductance kappa decreases, but the molar conductivity increases. And I told you why. Because molar conductivity is the product of conductivity and the volume of the solution. Though gradual decrease of the conductivity is observed, but side by side the volume of the solution increases by many times. So their product, molar conductivity of the solution, increases. After that, we studied separately the effect of dilution on molar conductivity. And we did the study separately for strong electrolytes and weak electrolytes. So we know in both the cases molar conductivity increases. So when you have taken the strong electrolyte, we have found gradually the molar conductivity increases with dilution. Then it was thought worthwhile, why cannot we study molar conductivity to infinite dilution? That is an imagination. Because you cannot dilute anything to the infinity level. And even if you dilute it, it is not experimentally possible to determine the conductivity, because the number of ions present per ml of the solution will be so less, conductivity meter will not be able to locate it. So we have taken the help of the graph. What about the graph that we have got for strong electrolytes on dilution? It is having a negative slope, and that line, with the help of a scale, we have extrapolated up to the conductivity axis. So we know on the conductivity axis, the value of all the concentration is always 0. That we have learned right from our lower classes about the graph. That is, wherever the extrapolated line has intercepted the conductivity axis, that is considered to be the conductivity at infinite dilution, or this is the highest conductivity ever can be shown by any strong electrolyte. So because of that, we also call it limiting molar conductivity. So we have found that we can determine the limiting molar conductivity of any strong electrolyte with the help of a graph. With this knowledge, we proceeded for the weak electrolytes. So in case of weak electrolyte, we have found the conductivity was increasing very slowly. And we started plotting it in a graph. Okay. That you know where from we got it? We got it from that Debye-Hooker-Onsager equation, that lambda m equal to lambda m0 minus a root over c. Okay. So we have found it was increasing gradually. But suddenly there is a steep rise in the conductivity, and this was running parallel to the conductivity axis. So in this case, it is simply not possible to find the conductivity of weak electrolyte because it is not going to intercept. So this experiment did not help us. So in that case, what thing we cannot get directly, we can get it by the indirect method. Okay? So we have gone for another method or theory, which is called the Colruy's law of independent migration of ions. Before I go to the theory, see, suppose I have taken here potassium chloride and sodium chloride. See, when the conductivity takes place, in that case, both potassium and the chloride ion, they move to the respective electrode. So conductance is not done alone by one ion. It is done by both the ions. So when I go for sodium chloride, we find the sodium ion and chloride, both of them they participate. But very interestingly, dear, you find the conductivity of chloride ion in potassium chloride and the conductivity of chloride ion in the sodium chloride is same. Is independent of the other ions or cations with which they are associated. So let me take another example. Suppose I have taken here potassium chloride and potassium nitrate. They are all strong electrons. In this case, we find the total conductivity of both of them is different, but the conductivity of potassium and both the salts are again same. So because of that, the law states that. So I will write down the law. At infinite dilution, when the dissociation is complete, means all the ions are free. Each ion makes a definite contribution towards molar conductivity of the electrolyte, irrespective of the nature of other ion, which it is associated. So this is the contrast. So write down this law. Now we write a simple law after that. The law in another way is simpler for us to remember. So below that you write or. Okay, now you write other one. The molar conductivity at infinite dilution for a given electrolyte can be expressed as the sum of the individual contributions from the ions of the ions of the electrolyte. If the limiting molar conductivity of cation is denoted by, see there, I write small lambda now. And that of an anion is then according to Colrush law of independent migration of iron. Yes, see, this is the our total molar conductivity of the whole electrolyte equal to nu plus lambda plus 0 and nu minus lambda minus 0. What is lambda plus and lambda minus? It is nothing but the number of cations and anions per formula unit of the electrolyte. So right now, where nu plus and nu minus is the number of cations and anions per formula unit of electrolyte. Okay. After this, then I'll explain to you. Moment to finish, please tell me. I cannot wait.
Hello. Hello.
Okay. So now I'll write the example. Then moment I write the example, it will be very easy for you. See, science is not that difficult, no. Whatever your level, it will be taught up to your level. You will not be taught anything which is much beyond your thinking capacity. Okay, see here. Suppose I have taken example. I have taken here sodium chloride. Sodium chloride dissolved in water. So what I will get here now? I will get here sodium and chloride. Why do I write aqueous? Because water molecules are surrounding. We call them hydrated ions. Okay, so I want to go for sodium chloride. Limiting molar conductivity of sodium chloride. See here, how many ions you have here? Sodium, 1 ion per mole. Sorry, not per mole. Per formula, 1 and 1. So in that case, what you write now here? See, this is for molecule, this is ion. You write now here Na plus 0 and Cl minus 0. In that case, what? Nu plus is equal to 1 and nu minus is equal to 1. So don't get nervous. So this is 1. I have gone for now barium chloride. Okay. So barium chloride, when it will dissociate, Ba2 plus aqueous. See, I'm not putting a reversible sign because it is a strong electrolyte. See here, it is nu minus is 2, nu plus is 1. So in that case, Ba Cl2 0 is equal to small lambda Ba2 plus and 2 Cl minus. So here nu plus is equal to 1 and here nu minus is equal to 2. Okay. Now suppose I have taken here aluminum sulfate, Al2 SO4 3. Okay. So right now here aqueous. So it will give you 2 Al3 plus and 3 SO4 2 minus. So Al2 SO4. Please write now. Write this. Write and tell me. What did you write here? Tell me. What did you write here?
2.
Yes.
Plus equal to
2 small lambda Al3 plus 3 small lambda sulfate. Now we'll see the application of contrast flow, that you please hear very attentively. Applications of contrast law. Okay. Now, contrast law, why is important? Let us see now. Determination of limiting molar conductivities of weak electrolytes. See, it's very interesting. Experimentally, we could not do, but with this law, we can find out the limiting molar conductivities of weak electrolytes also. Second, calculation of degree of dissociation of weak electrolytes. It's very interesting. Now, when you say weak theory will not help. We should know that how much percentage of acetic acid undergoes dissociation. How much amount of ammonium hydroxide goes to dissociation. Everything you can determine experimentally. And third is the calculation of dissociation constant of weak electrolytes. Please write first. Then after that we will do one by one. So now we'll go for the first. Write down the first one. Right below 1. Determination of limiting molar conductivities of weak electrolytes. Right. Okay. Then I start. So right now here, first we'll go with the example. Determination of lambda m0 of acetic acid means what? CH3COOH. All right. See, we know that weak electrolyte will not go for 100% dissociation at our ordinary condition. But if you have diluted to infinity, each and every molecule will break down 100%. Yes, it is a fact that we cannot determine it experimentally. But it is going to break into 100%. All right. So what we can think, we can write here at infinite dilution. What will happen? See here. Acetic acid molecule. I will not put reversible sign now. It is supposed to give me 100% dissociation. All right. If it is so, then according to Kohlrausch law, what should I write? Then, according to Kohlrausch law, what should I write? I have to write CH3COOH is equal to, see, 1 mole. So I'll write now here. CH3COO minus and this. All right. So you'll get this. Now, I have to now calculate, but experimentally I cannot find because the line, it goes parallel to the conductivity axis. It is not going to meet. Just like two railway lines do not meet each other, this also not going to meet each other. So we'll apply some technique. I'll write now. CH3COOH. Okay, I'll write this one. CH3COO minus and H. Sorry. H plus. Then dear, what you know what I'll do? I will add and subtract. Na plus and Na plus and Cl minus. I'm going to see. I have add and subtract. Then see what I'm going to do now. I'll take this one out. So I'll write now here CH3CO minus Na plus. Then I'll write now here H plus and Cl minus. Okay, so let me put it like this. Because everywhere plus is there, so now I have no problem. Minus Na plus and Cl minus. See, I can join this one because this is a molecule. I can join this one. It's a molecule. This is also a molecule. So, the moment it comes to molecule, this will not be some small lambda. It will be capital lambda. So, I'll write now here. This is CH3COO plus HCl minus Na. What I can write now? Therefore, lambda CH3COOH. This. See, it's very interesting. See how this mathematical equation could help people. It could help people. See there. This is a strong electrolyte. This is a strong electrolyte, and this is a strong electrolyte. So now, to find out the limiting molar conductivity of acetic acid, as I know the rule, I will make three solutions. What is the solution? I will make a solution of this. Okay. And I will measure. It's a strong electrolyte. I have no problem. I'll measure its this. See, then with the help of scale, I'll extrapolate. Then what is this? This is lambda m0 of this one. Similarly, I will make a solution of HCl. Okay, root over C. Sorry, lambda mc. Then with the help of a scale, I'll extrapolate. What is this? This is lambda m0 of HCl. Then I'll take sodium chloride. Okay, make solution of sodium chloride, and I will do the experiment. This. Then with the help of a scale, I'll extrapolate. What is this? This is lambda. So I have to do now three experiments. For this, sodium acetate, HCl, and sodium chloride. So I'll put these values. I'll immediately get the limiting molar conductivity of acetic acid. Okay, again I'm telling you. See, for weak electrolyte, experimentally, I cannot find the limiting molar conductivity because when you start diluting it, gradually the molar conductivity of weak electrolyte increases and suddenly there is a steep rise and we find the graph runs parallel to the conductivity axis. So in that case, we can never extrapolate this graph because it's not going to meet. So just like strong electrolyte, we cannot determine the limiting molar conductivity of weak electrolytes directly from the weak electrolyte. So we have taken the help of Kohlraasch law. So Kohlraasch law is applicable only at infinite dilution. So we know infinite dilution, any electrolyte, weak or strong, always goes for 100% dissociation. Because of that, I have written this and this. Now, according to Kohlraasch law, the limiting molar conductivity of acetic acid is nothing but the sum of the conductivity of acetate and the H plus ion. So I have written down. This is the Kohlraasch law. To that I have taken, it is not that you have to take sodium chloride. You can take potassium chloride or you can take any other electrolyte. So for simplicity, I have taken sodium chloride. So in that case, what did I do? I have added and subtracted this sodium chloride. And after that, I have simply rearranged it. After rearrangement, you find when you add both of them together, I get a strong electrolyte. When I added both of them, I get a strong electrolyte, and this is itself is a strong electrolyte. So this will do these 3 sets of experiments. As because they are strong electrolyte, we do not have any problem of the graph. We'll do 3 sets of experiment, put this value, and we'll get the limiting molar conductivity of weak electrolyte acetic acid. Please write. See, now we'll try to find out. This one I will not do. You will do it. Please find for ammonium hydroxide. So I will give you this hint. It will be NH4 plus and Cl minus. Exactly you write like this. Okay? Okay. Now, this one you change it and do exactly you follow. You will get this for ammonium hydroxide. Yes, you will do, I will not do it. So, NH4 plus and Cl minus. Then we'll add sodium chloride and we'll subtract. Now, I will not do anything else. Please do. Use your brain. Do. You write here. See, I'll write now NH4 plus. So you're going to combine with what? Plus will combine with minus. So what do we have here? Cl minus. I don't do your thing. Why you are taking so much of time? Okay, now see here. Now what do we have? Na plus. What negative thing you have here? Oh, sorry. OH. Ammonium hydroxide. Nah. Sorry. This. So, this. So Na plus will combine with this. Oh, it will be OH minus. So if I write both of them together, what do you get here? Ammonium chloride, sodium hydroxide. These are all strong electrolytes. So you get it by this method.